Hello everyone, today we're going to be going over the 2026 FU exam problem 7. This problem is about orbits and Lagrange points. So let's start by reading the problem. The James Webb Telescope lies at a point called the Lagrange point 2 or L2. This is a point where the telescope would remain stationary in a frame rotating with Earth's orbit around the sun. So a telescope placed exactly at L2 would be in an equilibrium position relative to Earth's orbit. What is the stability of this equilibrium point with respect to radial and tangential perturbations? Okay, so first of all, we need to understand what radial and tangential perturbations mean. So, you're expected to know these basic definitions, that radial is along the radius. So Earth's radius is this way, right? So this would be radial. And tangential is tangent to the direction of motion. So that's going to be in this direction. That is tangential. So let's start by drawing a free body diagram for the satellite. So this is the satellite at L2. First of all, we have a gravitational pull from Earth. So Fg from Earth. And we also have Fg from the Sun, right? And we also have a fictitious force in this, like in the inertial frame, that is the centrifugal force, which is equal to m omega squared r. Okay, so basically you have to have the centrifugal force balance the sun and the earth. So first let's check the radial. Let's check what happens if it is perturbated radially. So let's say that it's a bit too close to the Earth, okay? If it's closer to the Earth, then since Fg is equal to gmm over r squared, if r decreases, then Fg increases. So this way, the Fg in Earth and F sun will sum up to be greater than the centrifugal force, FCF. And that means that the net force will be in this direction. And that's more, that's going to make it unstable, right? Because then if the net force is moving toward Earth, then it will get closer and closer and eventually hit Earth. Now, so we can cross out the answer choices that say radial is stable. Stable to radial. Okay. So, this one, only C and D work, and E says that none of the listed. L2 is not a real equilibrium point because the centrifugal force is a fictitious force. Okay, so let me explain this. The centrifugal force is a fictitious force, but in the frame of the L2 point for the satellite, it acts as a force. So the fact is true, but the reasoning isn't right. Like, it's not just because it is a fictitious force that shows that it is not a real equilibrium point. Because we're in the inertial frame of the satellite. So there is an effective fictitious force. So now we know that it's not A, B, or E. So we just need to test the tangential perturbations. Now, let's say our satellite travels a bit higher up and it ends up right here. And we still have these. So now the gravitational pull from Earth is over here. and the gravitational pull from sun is here. Okay? Now, we also have the centrifugal force right here. And the centrifugal force always points outside. So what we notice right now is if I zoom in, these gravitational forces have a component. These gravitational forces have a component that points, it points downward, right? So while the centrifugal force does not, because it's just pointing away. So now, especially because so it's traveling with the sun's orbit, right? And the orbit is much farther away with a larger radius. So mostly the Earth's gravitational pull has this component that rarely impacts the satellite because it has like a significant extra amount of force that is making the satellite go back to this L2 equilibrium point. So if every time the satellite moves tangentially, it eventually comes back, that means it is stable. And if we look at our answer choices, it is stable to tangential perturbations and unstable to radial perturbations. So our answer choice is going to be C. Now, thank you for watching. If you have any questions, please ask in the comments below, and be sure to like and subscribe. Thank you.